usually because like fluid dynamics and simulations are really expensive to compute. So it's easier just to pre-compute the answers, and then you can just kind of send a whole bunch of bouncy balls down the stairs, and they follow around the flow field and like knock into each other, and they still form the same pattern. So you stumped the support guy. Good, good work. So now I'm actually going to have to figure out how in the hell to generate the flow field out of all the information I've gathered. So I'm going to be right back, and I'm going to start doing that. Yeah, well, good luck with the beta, and if that'll fix your problem with your blurs. And they'll come back and they'll be like, well, it doesn't have the same problem on my machine. What kind of graphics card do you have? And then like you find out that your graphics driver's at fault or something. We actually had that sort of thing happening when I was in college. We had one computer lab where it got a little bit too hot. All the machines did, and the graphics cards in the machines started to have lots of problems. and what would happen is like vertices that you wrote would go to infinity. So you'd be like playing your game, and then he already checked via remote desktop. Damn. You'd be playing your game, and a vert would go to infinity, so you'd see like this tear through the screen of like some animated mesh should be running along, and then like all of a sudden like things go flying out into space, and that was always insane. But so one of the issues with that is if you ever relied on any texture data to come back from after it's been processed on the graphics card, like it would just crash like all your stuff. And the professors, of course, never believed us when we're like, hey, these computers are a little shifty. Like this is all just garbage. These things don't work. And we called it getting Renoired because Renoir was the name of the computer lab. So we're like, ah, man, you just got Renoired when you're like playing, you're working on your game, and everything just like explodes and your thing crashes because of actual hardware failure. And so the professors never believed us, and that was really dumb until we had like this all school this school-wide game night, and like people in there were like playing Left 4 Dead 2 and like all that, and like they had all the same problems, and the professors were like, huh, well, maybe it is actually screwed up, and they had to replace like all the computers in the computer lab. But of course, they didn't fix the real problem, is that the room got too hot, and the cases they had for those computers were just garbage. But there were a lot of times, because people would be presenting their actual game in class, and it would just like fall apart and crash while they're presenting it. So like what my friends and I on my team, we would actually drag our own computers in when we had to present in that room and hook them up to the projector, and like, because we didn't want to embarrass ourselves. Anyway, let's come up with a plan for how in the hell we're actually going to make our flow field out of our information. So let's take this flow field and get our information. Let's construct our static height map. Let's save everything out here. What did you miss? You missed a whole bunch of just boilerplate garbage. We haven't actually gotten any interesting things done yet. So you missed nothing. Oh, you missed one guy asking if I could build his game for him. You missed that. I told him to go make a prototype. Figure out if it was fun. Alright, so we've got a whole bunch of textures here. So we've got like, I'll just open these. So we've got our height map, we've got our distance map, and we've got our texture simulation thing here. With all the information, we have all these particles. How the hell are we going to combine these together? We also have the inputs and outputs. Let me just write it down. What we've actually got here. Because I think we have all the information we need to actually construct our flow field. We just need to put it all together in a sane fashion and figure out what, because we've got all the information, right? We've got like, the density of the atmosphere, we've got the location of the planet, we've got how fast we're going in the space shuttle, and how much fuel we've got. We just need to figure out when we need to jump before we hit the ground so that we don't actually die. That's what we're trying to figure out right now. So what information do we have? We have inflow / outflow nodes. We have a calculated path for our main flow. We have particles. Those particles have history for where they've traveled. What else do we have? We have distance from shore. We have depth. We have yeah, that sort of thing. It sucked for what you wanted to do? Yeah. I think right now I've got two 980 GTX Ti's. I've been using that for a while. Yeah, just the GTX Ti's and all that sort of stuff. They work pretty well. I'm not super familiar with all the graphics card technology. Alright, what else have we got going on here that information that we know that we could use? We know the path, we know that, the shore. Got this, we got that. The normal on the bottom, the depth isn't really going to help us. So what sort of procedure should we do? Like steps to create flow field. Alright. So the flow field is going to be a direction. So what is the flow field? Let's see. Let's just try to organize this in our minds. So we have our input data, and we know what our output data should be. Our output data should be a map of directions and magnitudes for our flow. So we have a few questions about this. So for every location, we need to figure out the direction of the flow. We need to figure out the magnitude of the flow. What happened after you posted your Bradbury emote? I believe Karakan left, and then people are talking about graphics cards. Yeah, the only thing, Karakan, that the GTX 750 might not be able to do for you is render out your Harmony stuff. If that's working, then you're good to go, I'd imagine. Yeah, we're not going to be like you've been seeing how carefully I've been checking out to make sure that hardware compatibility isn't going to be a huge problem with our materials. So hopefully you don't have to buy a new graphics card for this game. And even hopefully, if we ever get, if after we launch everything on Steam, we can then, who knows, we might try to go to some other consoles like Switch or whatever. That would be my favorite one. If we could get this game on the Nintendo Switch, I'd be super happy. Alright, so we need to figure out the direction and the magnitude of the flow. So what would be our steps here? So what values do we absolutely know? things that we do know, like first pass would be like iterate through all calculated paths, set direction to current direction, set magnitude to max magnitude. So we have all these like pre-computed paths through this thing. So like this bright blue right here is this path that was through here. And we say like that's maximum flow. That's going to be our fastest point, and all the flow fields should be like that. Okay, then what we want to do is to I guess iterate through all particles, look at their history, average the historical direction, and direction is the average, yeah. This is the direction, and magnitude should be the distance traveled in history. Okay, so that's going to give us a whole bunch of gaps, though. Like, all this black stuff we're not going to have. So the question would be, what do we do after that? So we have, like, a whole bunch of data here. We have a lot of arrows. How do we spread those out? Do we just blur it? Do we blur everything? Do we blur pixels that haven't been written to? And then do a post-process blur over the top of that? I'm trying to visualize it. What would it look like? So if we took this picture right here, and do we want to use any of the distance to shore stuff? I don't think we actually care about the distance to shore stuff. I think we only care about this particle simulation. I mean, we could have like a distance from shore invert direction sort of thing, so that you never get like shoved directly into the shore. That there's like, okay, so that might be a good thing to pass in here. Go through all shore. Go through all pixels. If, well, shit. We have distance from shore, but we don't have the direction from shore, right? Like, we'd have to actually, like, go through all the pixels, and we'd want to look around them. So, like, if the pixel was shore, and the pixel to like, the bottom left of it or something, we could have, like, a 1 pixel outline of the shore. Like, if we imagined this as a 1 pixel outline, we'd have, like, a bright white or something right here, and we could have like a big value for that, and then we could smooth it out. We could then blur it, or have it shoot out a certain number or a certain radius with a direction and a magnitude, a small magnitude but a magnitude. So it would mean anything that like fell into the water would want to move away from shore just a little bit, just to kind of keep it off of stuff in case we've got other flow. Yeah, I think we definitely need that. Okay, so go through all pixels, detect hard shore edge, and right direction to surrounding pixels that are non-shore within radius. Magnitude is a constant small number. Okay, so that'll be the shore edge stuff. Keep it away from shore. I mean, we could do that first. We could actually do that as the very first pass, and other things could overwrite it. So that's kind of what I'm thinking of. Some of these things will blend together, some of these things will overwrite, some of these things will also not care. Like, some of these will be cumulative, some of them will be set. Like, the calculated paths, we can just set the value. I think we can set the values with all the particles. Okay, so what we've got right now is we have a short outline edge that's blurred. We've got all this stuff set with numbers. If we just did a whole... So what I'm trying to think of right now is a good way to fill in the gaps between our areas. So kind of the problem is, if we have like a blur on here, all of these empty squares are going to influence the areas that actually have data. And the question is, do I really want the empty squares to influence the data that much? So I'm trying to think of like what sort of blurring algorithm I would want. Because if I'm just taking samples around it, then it's not going to be super great. Let's say I did kind of a map sort of blur. So what I would do is I'd divide all this into grid squares that are exponentially smaller. So, and then kind of do a blur based on, I like average everything that's actually set in a tile, and it would average all the way up, and there's not going to be that many layers, 512, 256, 128, 64, 32, there's like going to be 8 layers or whatever of tiers. It's kind of a pyramid geometrical structure of math, which would blur stuff. And so if we just write the data that we have up into that layer, we'll get a pretty good data point, and we just fill in all the blank spots in the data with that tier. What tier would we fill it though with? Would we want like some sort of sum? So it'd be like each level needs to have a certain number of, like, this area is less dense, so it would take the highest level or a higher level of, or do we want like a constant, just like take level 3 and fill in all the gaps with that information? I think we just want to take a constant level. Alright, so do a tiered average with a specific level. So what this will be is, for every pixel right into the higher levels average, write the direction. Right, dir/mag into the higher level average, and for every blank pixel, grab the local average. Grab the local average. So what we'll end up having is grid squares. So areas would be divided into grids. Do we really want grids, or do we want something else? What actually is a mipmap? It's a pretty good question. So kind of how bitmaps exist is it's a concept with graphics. So it kind of comes from memory constraints. So like if this is our picture of something, right? Like this is our texture. Let's have something not awful. So like we've got our texture here, right? So, and this texture is in memory. So when you look at a texture, you're actually looking at a block of memory that, that exists physically. So when you have this texture and you pass it to your graphics card, that's what we use to render something to the screen. And when there's some issues with this though, like say, you've got your texture here and you blow it up real big, you can we can anti-alias and stuff, but when you make it real small, like you can see the text there as it gets real tiny, gets all pixelated and stupid. You don't really want that information to get kind of crunched together because then stuff doesn't look right, right? Like what you would want is instead of that, this is a texture kind of, if I make it real big again, it comes back. But, like an old MS Paint or something, this, yeah, see, if I copy paste it and I bring it back out, like it's information is lost and looks like garbage. So basically, when you create bitmaps, one of the things is you can, before, like when you create the texture, you want to create nice blended together smaller textures so that you don't have to sample stuff. Like when something is really small and far away on the screen, we can use these lower resolution textures to render them faster. And when you're real close, you want to use an entirely different texture, which is much more detailed. So when you're talking about bitmaps, what they do is you have these textures as a power of 2, and so you generate these textures that are, a quarter the size, like this. And when you lay these out in memory, like you can see kind of this pattern that I'm using here. Like I'm always making it the same size. You can see it fits real nicely, like right into this blob. So you always know with a bitmap, an array of a texture with all of its bitmaps, you always know it's going to fit into a chunk of memory that is exactly, this size. So it's a technique that really helps out with that. So it has a lot to do with stuff like that, and that's why they're power of 2 textures real important, because bitmaps will work better in memory and all this other garbage. So hopefully that gives you a little bit more of a physical understanding of kind of how they exist. But it's one of those Nautilus shell sort of things, which is a cool property of squaring sizes. Alright, so we're back here. For every blank pixel, we're going to grab the local average. So the question is, do we want a grid square sort of effect on this thing? Is it usually 1 to 2? Do you mean, is it usually 1 to, you have the mip-map be exactly half the size? I think that's just the definition of mip-mapping, is it's always, you have it half width and half height, so it's, fits in there. That's why it's also good to have, power of 2, because it can be divided by 2 cleanly, over and over and over and over again, so you don't get all sorts of weird crap going on. The INI auto determines if it's an int or not, and the game calls it. I guess the online subsystem grabs the ID from the config system, and the config system reads in the value as an int. Usually when you make a config system like that, it reads it in as like a variant. And when you ask it for an int, like in config systems I've written in the past, I wonder if Unreal does the same thing with it, where when you say get int, in config systems I've written, like if you had the value like 1.2 and you said get int on it, I'd just return 1, and if you said get float, I'd say 1.2, and if you said return string, I would return the characters 1.2. But I don't know if Unreal does it that way. That would be my guess, just because of systems I've worked in the past do that. Usually configs are trying to be kind of smart, but I have no clue. So the question is, do we want a grid square system on here? What would it look like? What would be the outcome of that? So if we had like this grid square up here, we would average and fill out all these things with, probably it would be in this direction, and then right here it would be like in this other direction. So if we have all these grids, basically boom, 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 and then we if we did like a blur over the entire picture, we would see a lot of we might be able to see the grid lines. So is there a better geometrical shape than a square which we could use, which would maybe not have the propensity of having so many stupid lines? Or is there some sort of other data structure which would hide a lot of these lines? Like maybe we have a 2-tier grid system where we average one and we average the other, and then we work it out. Oh, you had a mip mapping for the first resolution option. Well, it depends. Mip mapping can be done by the graphics card and like all sorts of other stuff, and turning it off would at least remove one operational step, because you're not sure if the mip map algorithm or whatever is blurring your, especially you're talking about Gaussian blur, right? And that's usually what mip mapping does, is it has a blurring algorithm for dealing with, fuzzing up textures. So maybe you're looking at a mip map of the source texture and not the actual texture. And that would explain like maybe a little bit of blurring artifacts. You know, if you weren't looking at level 0, you're looking at level 4. You know, that tiny little guy. If you're looking at this guy as opposing to this guy, then you might do something for you. And it might be like the size of your monitor or something that Harmony looks at to actually render that. Alright, so if we used a different hierarchy, like I'm thinking that if we use grid squares, we might be able to see grid lines for flow fields in our water. So I'm trying to think. Because we've got the shore map here. You know, the grid squares, the thing is that might be weird about grid squares is if the grid is too big, like if we were on the right side of this, you know, piece of land, we might affect the flow of water on this side of the piece of land, and that's not good. So it may be that instead of using grid squares, we do like some sort of discovery algorithm here, where we create our sub-object, our kind of average areas by growing, like inflating some sort of geometry to cover an area. So like, you know, if we just started trying to grow circles on this thing, you know, we would pick an area, like, you know, we're iterating over this in like a grid map fashion, you know, 16 by 16, and we just like put down circles and then we make them larger until like our circle hits shore, and then like we leave it alone. We might get like a circle here, a circle here. I should export this and take a look at it. Because I'm not sure what's going to look good for this sort of stuff. So let's think about this. So if we subdivide by grid squares, we'd have something that kind of comes out like, and I'm being slow with this on purpose. I'm kind of trying to think while I'm going over it and kind of look at what actually these grid squares are covering. So maybe this will help me visualize what's going on here. So, alright, Chris Goku, you have a good one, or whatever, if you're saying thank you because you're leaving. But, you know, glad I could help, well, at least a little bit. Alright, so if we took a look at these grid squares and we made them kind of big like this, this area would be moving away. This area would be moving towards. This would be kind of towards. Yeah, let's actually draw the arrows real quick that we would have. So this would be like, and then if we blurred them out, it seems like it might actually work out okay. Well, what if we used a two-tier system? Like if we offset it like this, then we would see things that look like we're averaging this one, which is this direction, and we're averaging this one, which is this direction. So it'd be like this direction. This one would be an average of this direction plus an average of this direction. So it'd be kind of like this. Alright, so this would be an average of this direction with an average of I think a two-tier system, a two-tier average would probably do it. Actually, I could do like an exponential fall-off average with the MIP of the thing, and that might actually work better than anything else. It's kind of like a whole field blur. And we could weight it by something. We could do like a level weight. Alright, so alright, do a tiered average for every level. Weight the level by a level weight modifier. Is this exponential or linear? All right, so we'll do this tiered blur thing for everything, and we'll go all the way up the chain. And then I guess we have to do a whole screen blur on the output. It's like we've got all these. We now have every single pixel with a direction and a magnitude. We now want to blur that thing. Now the question is, how should we actually blur it? We could do like a whole picture blur, kind of the Gaussian blur sort of, crappy blur sort of thing. Take all the surrounding nodes and add them all together. What would it look like though? What are the artifacts that are going to happen because of just a straight blur? We'd wash out our larger areas with a strong blur. I mean, we could do a blur, like a kind of a general blur pass, which blurs everything that wasn't set specifically by a particle or by a path. Therefore, we wouldn't blow away a lot of our data. And we could actually blur pretty heavily on that. So we do like a rough blur on the guess average set pixels, and that'll smooth everything out. It'll also take into account the shore stuff, so the shore stuff will be blurred away from the shore. And then we do a finer blur, and we blur everything. So we do a rough blur pass, but we don't use that, and then we do right. So rough blur pass, blur all pixels with surrounding pixels, except skip things set by particles or paths. And then we do a fine blur pass, blur everything. And at the end of that, I think we'll have our flow map, our flow field. I can see it now in my mind's eye. Can't see anything. I don't know what I'm doing. Alright, well, I think I have a plan on what the hell to actually implement here. So, I'll be right back and I'll start on it. So what are you saying? You're saying you think you can make water shaders now. You have a 512 by 512 texture, turns into 1024. You have a colored square in the middle. Simply times that by 2 to get an acceptable difference. Yeah, the UVs just go from 0 to 1. So, and they're based on the vertex geometry. So when you're in the middle, it's just going to be a 0.5, and then it just looks up into the texture at a 0.5, and it'll read that data out. Yeah, that's kind of how that's how the vertex values get interpolated using hyperbolic coordinates and all that stuff. So you don't have to calculate any of that yourself. You just say what the vertex is supposed to be, like 0 or 1, and when it rasterizes the triangle, all the pixels will get their stuff calculated properly for you. Yeah, you don't need any matrix math unless you're doing something else. Alright, well, let's start implementing this thing then. Alright, so Step 1, go through all pixels, detect a hard shore edge. So let's do it. So let's call right shore edge. So RGB is going to be XYZ. And let me think, we're going to need world space in this thing. So let's remember that we're going to need world space. So we need to convert from this XY space into world space. Now the question is, should we do that at the end? Yeah, I think we'll do it at the end. Alright, so I'll put step 7 here. Convert to world space.